Hello and welcome to another video on this time Oxford Math 2015 questions A to E. I'd like to point out this 2015 paper seems to have the lowest score, one of the lowest scores, looks like the lowest average score really for quite some time out of all of them. So obviously this paper was supposed to be the toughest, so if you are finding 2015 difficult, well, most other people did by the looks of things. I think like they're really transparent, both the step and the map papers, sorry, in terms of like what you need. The feedback is really useful to go into. If you ever go into that, I love the little graph they do of like the people who received an offer, the people who were interviewed and not shortlisted, and the people who were not shortlisted at all. You can see like what kinds of scores was getting you in, and it's always quite amusing to see somebody, get like 85 to 89% and not get an interview. Well, I say amusing. I don't mean that in a nasty way. I just mean like, what do people have to do? Maybe their interview just went catastrophically wrong. I don't know. Who knows? Or maybe they weren't really interested and they want to go somewhere else. Anyway, let's get on with the MAT 2015 questions A to E. So I thought this, certainly the short questions, I thought towards the start, I actually preferred the ones towards the end, which is weird, but towards the start, I actually found some of these quite tough. This kind of question, it's pretty obvious. It's probably wise to write it out in algebra. Square the answer, times by 4, subtract 3. So that's what we're actually doing here. Which of the following statements are true, regardless of the starting number chosen? So, okay, first thing I thought was the final answer is definitely going to be odd, yeah? And that's because this bit's even, and even minus odd is always odd. So that one's true. So anything without a 1, you can forget about it straight away because that one's definitely true. Final answer is 1 more than a multiple of 3. I thought, is that always true? I think it can be a multiple of 3. If I make sure I pick x such that after squaring, adding 1, squaring it, it equals a multiple of 3. Well, a multiple of 3 minus a multiple of 3 is a multiple of 3. So I don't think that it's always 1 more than a multiple of 3 regardless of the number chosen, because if I chose x is 2, I'd get 36 minus 3, 33, and that is not 1 more than a multiple of 3. So that's false. Final answer is 1 more than a multiple of 8. So like a multiple of 9 or something like that. Well, I think if I just use that last answer, picking x is 2, we get 33 at the end. Okay, that is 1 more than a multiple of 8, but what about picking x is 3? Then we're going to get 4 squared, which is 16, 64, minus 3 is 61. Let me just check I've done that right. Yep, that looks right. That is not 1 more than a multiple of 8. That's 5 more than a multiple of 8, so that's wrong. The final answer is not prime. I'm pretty sure that I can make it prime if I pick x equal to 1, because I'm going to get 2 squared, which is 4 times 4 is 16. It goes to 13. So that's wrong. At this point, it should be obvious that the answers 1 and 5. I just thought I'd quickly prove to you that the final answer is not 1 less than a multiple of 3. Shall I prove to you that that can't happen? Okay, so obviously x plus 1 is either 3p, 3p plus 1, or 3p plus 2. Yeah, I wouldn't do this in the exam because I would have already established it was E and I'd be moving on to the next one. But just to kind of prove it, okay, if x plus 1 is 3p, then this is going to be a multiple of 3, which is not 1 less than a multiple of 3. Yeah, so that's pretty obvious because you're going to get 3p all squared times by 4 minus 3, which is, the key thing is it's 4 times by 9p squared minus 3, which is clearly a multiple of 3. So when you start with a multiple of 3, you finish with when x plus 1 is a multiple of 3, then the final answer is a multiple of 3. Now let's say x plus 1 was instead 3p plus 1. You're going to get 3p plus 1 all squared minus 3. And I just want to show you that it's not 1 less, it's actually going to be 2 less than a multiple of 3, or if you prefer 1 more than a multiple of 3. Because you're going to get 4 times 9p squared, you're going to get a 6p times 4, so that's 24p. And then you're going to get a plus 4 minus 3, which is a plus 1. Do you see what I mean? Because that's clearly a multiple of 3. That's 1 more than a multiple of 3. So the answer is either a multiple of 3 or 1 more than a multiple of 3. Or let's try the very last situation, 4 times 3p plus 2 squared. Like I say, I would never do this in the exam conditions because you haven't got time to do this. But I just wanted to prove it to you. So you're going to get 4 times 9p squared plus 4 times 12p, which is 48p. And then you're going to get plus 4 times 4, which is 16, but minus 3, 13. But 13 is, of course, plus 12 plus 1. So that's one more than a multiple of 3. One more, see? So just proving to you there that it's not one less than a multiple of 3. It's either a multiple of 3 or one more than a multiple of 3. You could probably do that with modular arithmetic as well, because it feels very modular arithmetic-y to me. Okay, this was a weird one, because you kind of wonder, like, you know, how am I going to do this? Should I try sketching the graph? I actually just differentiated it in the end. And I think what confused me was I thought, well, the number of intersections is always going to be 2. So always even. I mean, that ends up being the right answer. But, you know, it just seemed to me like, why wouldn't they say 2 if that's a more precise way of putting it? Because if f of x is x plus a to the m, then f dash of x is, by chain rule, if you like, n times x plus a to the m minus 1. And so if I'm finding where they intersect, let's just make them equal. Now you could divide through by x plus a to the n minus 1, but it's ill-advised because you lose solutions there. You should always factorise in this situation. So take it over here to avoid yourself missing the solutions where the brackets equal 0, and then factorise. So x plus a to the n minus 1 multiplied by x plus a minus n equals 0. This gives us two solutions. X equals minus a, or, well, two distinct solutions. X equals, I guess, n minus a. Yeah? Now, because n is greater than or equal to 2, this can't be the same as this one, if you see what I mean. Well, I suppose you've got a situation where n is a positive whole number. Okay, so, sorry, yeah, n is a positive whole number, and a is a real number. I'm just trying to decide if these solutions can ever coincide. Well, minus a equals n minus a in the case where n equals 0. And only in that situation, but n is greater than or equal to 2. So these can't be the same number. And so we just get two solutions, two distinct points of intersection. And therefore it's always even. Done. Didn't like the way it put it though. Like, you know, I was agonizing over this one a bit, saying, oh, is it dependent upon a? But no, of course, this is just, you know, a cubic moved, you know, to the left by a vector a0. Okay, let's try this one. I quite like this one, I'll be honest with you. This one wasn't really stressing me out. First one I thought was wrong is this one. It's not true for all x, because straight away you can write that as a half sine 2x. You want to know your double angle for this, it makes it a lot easier. And they're saying that that's always less than or equal to a quarter. Well, that's false, because I can pick a value for x which makes that a half, because where does sine achieve its maximum? Pi over 2. So if 2x is pi over 2, then x is going to be pi over 4. So x equals pi over 4. I think we get a half from this, and you can see it over here. Sine of pi over 4 is 1 over root 2. 1 over root 2, multiply them together, you get a half, and a half is definitely bigger than a quarter, so that's false. I just looked at that one straight away and thought, ah, that's false, because we're trying to decide which ones are true. What else was false? Let's have a look at this one at the top. Yeah, you could use compound angle on these. You seriously could, or you could just think about the graph transformation. Should we do graph transformations? Well, actually, I think the first thing I thought was cos of 90 minus x is sine x. Yeah, that's what that actually equals, this bit here, sine x. That's a really good result to know. Sorry, you've noticed in my other videos, I expect, I always switch between radians and degrees as if it doesn't matter. It does matter, but in these multiple choice questions, I guess it doesn't matter. So 90, I mean pi over 2. Those are really important identities to know. You should be aware of them. Really, it's just saying in a right-angled triangle, when you switch from this angle, well, let's call it x, to the other angle, you obviously got x and 90 minus x. And that's a way of switching the opposite and the adjacent. Yeah, the hypotenuse always stays in the same place, but you know, sine x is a over h here, and cos of 90 minus x is a over h here, you know, and vice versa. So it's a really important one to know. Now, is sine of pi over 2 plus x always the same as sine x? Definitely not, because that moves the sine x graph like 90 degrees to the left, and so this is false. You could absolutely do this with compound angle formulae, yeah, by expanding both sides. And two I think is true, just because. Now, how did I do this? Oh yeah, rewrote cos squared as 1 minus sine squared. And apologies if I'm using techniques. Can I just let s equal sine x here? It's so much easier, especially on these ones where you've got not much time. Let s equal sine x. Yeah, you're going to have 2 plus 2s minus 1 minus s squared. I thought I'd write it down like that first, and we want to decide if this is always greater than or equal to 0. Okay, what is that going to give us? It's going to give us s squared plus 2s, and then we've got 2 minus 1. Well, that's plus 1, greater than or equal to 0. Hang on, that's a perfect square. So that is definitely greater than or equal to 0, because squares are always 0 or bigger, and so it's greater than or equal to 0. So that's true. So it looks like the answer's 2 or 2 and 3, but as you can see, I'm in a position to judge, because I've already established this as false, that it's 2 and 3. But just to prove you 3 is true, you can think about it with graphs. Do you want to? Maybe it's better I do it with graphs, because they do expect you to do this without any A2 mathematics. So, maybe I won't use compound angle formulae, but if you know compound angle formulae, it's quicker. So, it's a good one to know. And as you can see in these videos, I don't necessarily, I've already established the answer now, but I just want to explain why some other answers are false, just in case you're wondering. Okay, that moves the graph back 3 pi over 2, doesn't it? Because this occurs at 3 pi over 2. Basically, the sine graph's going to move back to here, and so you're going to get what looks like a sort of upside down cos graph. Yeah, that's what that one looks like, that side. Well, what about a cos of pi minus x? Well, cos of pi minus x, what does that actually do? If we're going from cos x to cos of pi minus x, I suppose the first thing we want to do is go from cos x to cos of minus x, if you like. This is one way of thinking about it. Cos x to cos minus x means the x coordinate is going to go from positive to negative, but on a typical cos graph, that doesn't change it. Yeah, because if you reflect cos in the y-axis, nothing happens. Yeah, and then we've just got to do cos of minus x, which we're already at. We've got to take that to cos of minus x add pi. Now, am I doing this in right order? Let me just think. I don't. I've got to be careful with these. You've got to be really careful, because you always attack the x. I kind of feel like that's not going to move it pi. I don't think it will matter, because the x and the minus x are exactly the same. I think I should have done the transformation the other way around, moved it x minus pi, and then. But I think it will work anyway, but I don't want to confuse you. Can I start again on my cos x transformations? Because actually what we want to do first is take it from cos x to cos of like x minus pi, and then I'm going to change it to or x plus pi, and then I'm going to attack the x and yes, reflect it. Okay, so if I do it this way round, I think it might work both ways around, but you've got to be careful here. We always attack the x when we're moving in this direction, so that moves cos x back by pi. Now, bearing in mind it reaches its nadir at pi, it's its bottom at pi. That's just going to move it so it suddenly looks exactly like this one. Yeah, and then cos of minus x plus pi, well, we've attacked the x and changed it from positive to negative, so that's going to reflect in the y-axis, and it's going to be exactly the same as the one over here. So it's going to be the same, but it's a lot easier if you just use compound angle formulae, I think, in some ways. But anyway, the answer is C, 2 and 3. D. Okay, what have we got here? I just directly integrated these. I didn't like the fact that x was in there, because it's like a variable, but is it a variable? Well, I just thought, well, if I'm working out f of 2, I'd have 2t all squared dt. If I'm working out f of 3, I'd have 3t all squared dt. And that would function like a constant, which I could take out, after squaring it. So the way I figured it was f of x is going to be equal to, and I did just directly integrate this, x squared t squared dt between 1 and 0. Well, that's x squared t cubed over 3 between 1 and 0. And so that's going to be x squared over 3. G of x, and you can always do this in your head, t cubed over 3, plugging in x, plugging in 0, you're going to get x cubed over 3 for that one. And there we go. We've got f of x and g of x. And then I thought, well, what's f of a and g of a then? Well, it's exactly this. So now I can work out gf of a and fg of a. And all of them are about gf of a and fg of a. So gf of a is just going to be a squared over 3. And then I'm going to need to cube it and divide it by 3. That equals a to the 6 over 3 cubed is 27 divided by 3, 81. F of g of a. Well, that's plug g into f. So we're going to have a cubed over 3. But then we're going to be squaring that and dividing by 3. And that's a to the 6 over 27. Yeah. Now, I did get slightly concerned about if a was less than 1 or bigger than 1, mainly because they were talking about in the question. But then I thought, hang on a second, they've both got an a to the 6 in there. So, of course, the numerator is going to be identical regardless of the value of a. And therefore, this one, because it's got a smaller denominator, must be bigger. And so f of g of a is always bigger than g of f of a. Yeah, a is strictly bigger than 0 as well, so it's not like they can be equal because a is bigger than 0. But it's got nothing to do with the value of a because the a's, if you like, cancel. So g of f of a, f of g of a is always bigger than g of f of a. Okay, E, where are we? Okay, so these are classics as well. Watch out, whenever you invert a sine or a cosine, you get more than one answer, don't you? That's the thing to remember. So when you get 2 cos 2x plus 2, which is definitely what I did first. I did inverse sine of 0. You get 0 or pi or 2 pi or 3 pi or 4 pi. I like emphasizing to students, you get infinite answers when you do inverse sine, inverse cos, or inverse tan. Watch out for that. Yeah. Now, only some of these I'm going to be interested in because I need answers. I'm only interested in answers which are produced after I take away 2 and then divide by 2, yeah? So let me just have a look at what cos 2x equals. So what I'm going to do is take away 2 from these and divide by 2. Take away 2 and divide by 2. Take away 2 and divide by 2. Take away 2, divide by 2, take away 2, divide by 2. Dot, dot, dot. Now, the reason I did a few there was because I know that cos can only be inverted if it's inverting on a number between 1 and minus 1. Yeah? Well, there's minus 1, and that's actually greater than minus 1 if we consider pi is about 3. And I often use approximations in these papers. This is like minus 5 over 2. So ignore these. That gets more negative as well down that end. Pi is about 3, minus 2 is 1, 1 divided by 2 is a half, so I need that one and I need that one. But 2 pi minus 2, well, that's about 6 minus 2, which is 4, divided by 2, which is 2. So they're just going to get bigger from there. So these are the only two I can invert. Now, how many solutions are you going to get when cos 2x equals minus 1? Well, not that many, because remember, we're dealing with this range, and that means that 2x will be trapped between 0 and 4 pi. Yeah? If x is trapped between 0 and 2 pi. So how many times does cos 2x equal minus 1 between 0 and 4 pi? Just twice. Yeah, there's 4 pi. It happens at pi and at 3 pi. You get minus 1. So there's just 2 solutions there. And that's like the edge case where it equals 1 or minus 1, where you get, not just a typical 2 or 4 or 6 or 8. Now with cos 2x equals pi minus 2 over 2, I don't have to go through the awkward work here. I know this is some positive number between 0 and 1. I know it's roughly equal to, if you like, 3 minus 2 is 1. It's roughly equal to a half. So how many times does cos 2x equal a half in that range? 4 times. Once, twice, 3 times, 4 times. And so you get 4 solutions out of this one. And so the answer is 6 solutions. That's how I did that one. Sort of like a bit of common sense sort of maths logic. Okay, so I'll do the next 5 as well in a second. I'll pop it up. I've just got to do a little bit of tuition with somebody coming round. But yeah, I'll do the next 5 very, very soon. But keep up the hard work for the mat and best of luck. And I'll try and get the big questions done as soon as I can. Bye-bye.